More the salt content in the soil, less is the water available to the plant. Classification of soil water. Soil water has been classified from a physical and biological point of view as physical classification of soil water and biological classification of soil water. 1. Physical classification of soil water. I. Gravitational water. 2. Capillary water. And 3. Hygroscopic water. 1. Gravitational water. Gravitational water occupies the larger soil pores, macropores, and moves down readily under the force of gravity. Water in excess of the field capacity is termed gravitational water. Gravitational water is of no use to plants because it occupies the larger pores. It reduces aeration in the soil. Thus, its removal from soil is a requisite for optimum plant growth. Soil moisture tension at gravitational state is 0 or less than first March atmosphere. 2. Capillary water. Capillary water is held in the capillary pores, micropores. Capillary water is retained on the soil particles by surface forces. It is held so strongly that gravity cannot remove it from the soil particles. The molecules of capillary water are free and mobile and are present in a liquid state. Due to this reason, it evaporates easily at ordinary temperature. Though it is held firmly by the soil particle, plant roots are able to absorb it. Capillary water is, therefore, known as available water. The capillary water is held between 1st March and 31 atmosphere pressure. 3. Hygroscopic water. The water that held tightly on the surface of soil colloidal particle is known as hygroscopic water. It is essentially non-liquid and moves primarily in the vapor form. Hygroscopic water held so tenaciously, 31 to 10,000 atmosphere, by soil particles that plants cannot absorb it. Some microorganism may utilize hygroscopic water. As hygroscopic water is held tenaciously by surface forces, its removal from the soil requires a certain amount of energy. Unlike capillary water, which evaporates easily at atmospheric temperature, hygroscopic water cannot be separated from the soil unless it is heated. 358 1827, Shankar IAS Academ. Hygroscopic water. Capillary water. Gravitational water. Water adheres to soil particles. Water held in large pores available for crop use. Water drains through soil profile. Wilting point 15 bars. Field capacity 1/3 bar 2. Biological classification of soil water. There is a definite relationship between moisture retention and its utilization by plants. This classification based on the availability of water to the plant. Soil moisture can be divided into 3 parts. I. Available water. The water which lies between wilting coefficient and field capacity. It is obtained by subtracting wilting coefficient from moisture equivalent. 2. Unavailable water. This includes the whole of the hygroscopic water plus the part of the capillary water below the wilting point. 3. Super available or superfluous water. The water beyond the field capacity stage is said to be super available. It includes gravitational water plus the part of the capillary water removed from larger interstices. This water is unavailable for the use of plants. The presence of super available water in a soil for any extended period is harmful to plant growth because of the lack of air potential. Hygroscopic water. 31 Wilting point 15 field capacity 0.33 saturation. D bars. Solid unavailable CSL so raw available superfluous form. Hygroscopic water. Capillary water. 359 Gravitational water. 1827. Soil moisture constants. Earlier classification divided soil water into gravitational, capillary and hygroscopic water. The hygroscopic and capillary waters are in equilibrium with the soil under given condition. The hygroscopic coefficient and the maximum capillary capacity are the 2 equilibrium points when the soil contains the maximum amount of hygroscopic and capillary waters, respectively. The amount of water that a soil contains at each of these equilibrium points is known as soil moisture constant. The soil moisture constant, therefore, represents definite soil moisture relationship and retention of soil moisture in the field. The 3 classes of water, gravitational, capillary and hygroscopic, are however very broad and do not represent accurately the soil-water relationships that exists under field conditions. Though the maximum capillary capacity represents the maximum amount of capillary water that a soil holds, the whole of capillary water is not available for the use of the plants. A part of it, at its lower limit approaching the hygroscopic coefficient, is not utilized by the plants. Similarly, a part of the capillary water at its upper limit is also not available for the use of plants. Hence 2 more soil constants, viz., field capacity and wilting coefficient, have been introduced to express the soil-plant water relationships as it is found to exist under field conditions. 1. Maximum water holding capacity. It is also known as maximum retentive capacity. It is the amount of moisture in a soil when its pore spaces, both micro and macro capillary, are completely filled with water. It is a rough measure of total pore space of soil. Soil moisture tension is very low, between 1/100th to 1/1000th of an atmosphere. 2. Available water capacity. The amount of water required to apply to a soil at the wilting point to reach the field capacity is called the available water. The water supplying power of soils is related to the amount of available water a soil can hold. The available water is the difference in the amount of water at field capacity, 0.3 bar, and the amount of water at the permanent wilting point, 15 bars. 3. Field capacity. Assume that water is applied to the surface of a soil. With the downward movement of water, all macro and micro pores are filled up. The soil is said to be saturated with respect to water and is at maximum water holding capacity or maximum retentive capacity. It is the amount of water held in the soil when all pores are filled. Sometimes, after application of water in the soil, all the gravitational water is drained away, and then the wet soil is almost uniformly moist. The amount of water held by the soil at this stage is known as the field capacity or normal moisture capacity of that soil. It is the capacity of the soil to retain water against the downward pull of the force of gravity. At this stage only micropores or capillary pores are filled with water and plants absorb water for their Arcana Graj. 360. 1828. Use. At field capacity water is held with a force of first March atmosphere. Water at field capacity is readily available to plants and microorganisms. 4. Wilting coefficient. As the moisture content falls, a point is reached when the water is so firmly held by the soil particles that plant roots are unable to draw it. The plant begins to wilt. At this stage even if the plant is kept in a saturated atmosphere it does not regain its turgidity and wilts unless water is applied to the soil. The stage at which this occurs is termed the wilting point and the percentage amount of water held by the soil at this stage is known as the wilting coefficient. It represents the point at which the soil is unable to supply water to the plant. Water at wilting coefficient is held with a force of 15 atmosphere. 5. Hygroscopic coefficient. The hygroscopic coefficient is the maximum amount of hygroscopic water absorbed by 100 g of dry soil under standard conditions of humidity, 50% relative humidity, and temperature, 15 degrees Celsius. This tension is equal to a force of 31 atmospheres. Water at this tension is not available to plant but may be available to certain bacteria. Types of soil moisture Ho unavailable for plants soil particles with forms of soil moisture O available Ho hygroscopic Ho capillary Ho gravitational Ho wilting point saturation. Note, some capillary water is bound to hygroscopic water on soil particles and is also unavailable. Field capacity gravitational water 361 1828. 7. Soil AIR. Soil atmosphere is the gaseous phase of the soil. Soil air occupies the pores which are not occupied by the liquid. Soil air is a continuation of the atmospheric air. It is in constant motion from the soil pores into the atmosphere and from the atmosphere into the pore space. The exchange of gases between the soil pore spaces and the atmospheric air is known as soil aeration. Soil aeration is essential for the respiration and survival of soil organisms and plant roots. This process controls the deficiency of oxygen consumed during respiration of plant roots and soil microorganisms and prevents toxicity of carbon dioxide evolved during respiration in the soil air. Composition of soil air. Soil air contains gases like nitrogen, oxygen, carbon dioxide, water vapor, and others. The composition of soil air is different from atmospheric air. Soil air contains more carbon dioxide and less oxygen than atmospheric air. It also contains more water vapor than atmospheric air. The nitrogen content of soil air is almost equal to atmospheric air. Air capacity. This term is used to describe aeration status of soil. The air capacity refers to the volume of pore space filled with air when the soil under a tension of 50 millibar. The aeration capacity can be characterized in three ways as given below. 1. Content of oxygen and other gases. 2. Oxygen diffusion rate, ODR. It is the best and most reliable measurement of aeration capacity. It determines the rate at which O in soil air is replenished. ODR decreases with soil depth. ODR should be above 40 x 10 gcm superscript 3 minute for good growth of most of the crops. However, the root growth is drastically reduced when the ODR decreases to about 20 x 108 gcm superscript 3 minute. 3. Oxidation, reduction potential, A, of soil. It is an important chemical characteristic of soil related to soil aeration. It indicates the oxidation and reduction states of soil system. In oxidized soil, ferric, Fe superscript 3 asterisk, manganic, Mn, nitrate, No, and sulfate, so too, ions dominate. In reduced soil, ferrous, Fe superscript 2 asterisk, manganese, Mn superscript 2 asterisk, ammonium, NH asterisk asterisk, and sulfides, S2, are present. The redox potential is measured using platinum electrodes and expressed in millivolts. A positive A value indicate oxidized state and a negative A value indicate reduced state. 362. 2133. Factors affecting soil aeration. 1. Amount of airspace. The topsoil contains much more pore spaces than the subsoil, thus the opportune for gaseous exchange is more in the topsoil than in subsoil. Hence the oxygen content of the topsoil is greater than the subsoil. The soil properties such as soil texture, bulk density and aggregation affect the amount of pore space and hence the soil aeration. 2. Soil organic matter. When organic matter is added to the soil, it is readily decomposed by the microorganisms to liberate the CO in soil air. Thus the concentration of both O and CO are affected by microbial decomposition of the organic residues. Besides, the respiration of higher plants and the microorganisms around the roots is also a significant process affecting the soil aeration. 3. Soil moisture. The macropores are filled up with water immediately after heavy rain or irrigation and level of oxygen content falls to zero. When the soil is artificially drained again, the macropores are filled up with air and the oxygen content of the soil increases. 4. Seasonal differences. There is a considerable seasonal variation in the composition of soil air. In the springtime in temperate humid regions the soils are wet and cold and the gaseous exchange is poor. In summer months, when the soils are dry, the gaseous exchange will increase. This will result in relatively high content of O and low CO2. Renewal of soil air. 1. The exchange of gases between the soil air and the atmosphere takes place mainly by the following two mechanisms as given below. 1. Mass flow. The mass flow occurs due to total pressure gradient of gas. The pressure gradient causes movement of entire mass of air from a zone of high pressure to that of low pressure. Such a flow of air occurs within the soil or from atmospheric air to soil air or vice versa. When the soil temperature is higher than the atmospheric temperature during midday, then the soil gases will expand and move out of the pore space into the atmosphere. 363. 2134. When the soil is cooler than the atmosphere during night, then the atmospheric gases enter the soil. When the atmospheric pressure is high, the atmospheric gases will enter into the soil. 2. Diffusion. The gaseous interchange between the soil and atmosphere takes place by diffusion. It is the process by which each gas tends to move in the space occupied by another as determined by the partial pressure of the gas. The partial pressure of ounce is higher in the atmosphere than in soil pore space, and the partial pressure of core is higher in the soil pore space than the atmosphere. However, total pressure both in the soil and the atmosphere may be the same. Thus ounce will move into the soil and the core will move out of the soil. The renewal of gases by mass flow is less important than the diffusion in determining the total exchange that occurs between soil and the atmosphere. 8. Soil temperature. Soil temperature greatly affects the physical, chemical and biological processes which occur in the soil. Since, with every 100 C rise in temperature, rate of chemical reaction get almost doubled, hence, it affects plant growth directly and also indirectly by influencing moisture, aeration, structure, microbial and enzyme activities, rate of organic matter decomposition, nutrient availability and other soil chemical reactions. Sources of heat to soil. Solar radiation, sun rays, is the primary source of energy to warm the soil. The dust particles, clouds and other suspended particles intercept the sun rays. They absorb, scatter or reflect the solar energy. Only a small part of the total radiation actually reaches Earth. Thermal energy is transmitted in the form of thermal infrared radiation from the sun across the space and through the atmosphere. Other sources of heat for soil are processes like microbial decomposition of organic matter and respiration by soil organisms including plants. 364. 2135. Factors influencing soil temperature. There are three main factors affecting soil temperature as described below. 1. Solar radiation. Amount of solar energy received by soil depends on the constituents of the atmosphere. Clouds, water vapor and dust particles reduce the solar energy reaching soil surface. Some energy is used for evaporation and transpiration, and some reflected back. Only 10% energy is used to warm the soil. 2. Aspect and slope. The land in three situations with southern aspect, level and northern aspect receive different amounts of solar energy, and the soil will warm accordingly. Solar radiation reaching perpendicular to the soil surface will heat it more as these concentrate on a smaller area than when the same amount of radiation reach a slope where they get spread on a larger area. Thus, equatorial zones are warmer than temperate and Arctic regions. In northern hemisphere, south-facing slope is warmer than the north-facing slope. 3. Soil factors. These factors are soil color, soil moisture, mulching, vegetative cover and organic matter content. These affect the warming of soils through solar radiation. 365 2135. 4. Soil chemical properties. 1. Soil colloids. The colloidal state refers to a two-phase system in which one material in a very finely divided state is dispersed through second phase. The examples are solid in liquid, dispersion of clay in water, and liquid in gas, fog or clouds in atmosphere. The clay fraction of the soil contains particles less than 0.002 mm in size. Particles less than 0.001 mm size possess colloidal properties and are known as soil colloids. General properties of soil colloids. 1. Size. The inorganic and organic colloids are extremely small size, smaller than 2 micrometers in diameter. These particles cannot be seen using an ordinary light microscope but can be seen only with an electron microscope. 2. Surface area. Because of their small size, all soil colloids have a larger external surface area per unit mass. The external surface area of 1 g of colloidal clay is 1000 times that of 1 g of coarse sand. Certain silicate clays have extensive internal surfaces occurring between plate-like crystal units that make up each particle and often greatly exceed the external surface area. 3. Surface charges. Both external and internal surfaces of soil colloids carry negative and or positive charges. Most of the organic and inorganic soil colloids carry a negative charge. When an electric current is passed through a suspension of soil colloidal particles, they migrate to anode, the positive electrode, indicating that they carry a negative charge. The magnitude of the charge is known as zeta potential. The presence and intensity of the particle charge influence the attraction and repulsion of the particles towards each other, thereby influencing both physical and chemical properties. The sources of negative charge on clays comes from ionizable hydrogen ions. 2. Isomorphous substitution. Ionizable hydrogen ions. These are hydrogen from hydroxyl O ions on clay surfaces. The LO or SiO portion of the clay ionizes the H and leaves an unneutralized negative charge on the oxygen, alloy, SiO. The extent of ionized hydrogen depends on solution pH, and hence these negative charges are pH-dependent charges. More ionization occurs in alkaline, basic, solutions. 2. Isomorphous substitution. This is due to the substitution of a cation of higher valence with another cation of lower valence but similar size in the clay crystal structure. In clay crystals, some ions fit exactly into mineral lattice sites because of their convenient size and charge. Dominantly, clays have Si4+ in tetrahedral sites and L superscript 3 in octahedral sites. Other ions present in large amounts during clay crystallization can replace some of the L and SIT asterisk cations. 366. 2144. Common substitutions are the Si4+ replaced by L, and replacement of all, by Fe Mg superscript 2 or Zn superscript 2. As the total negative charge from the anions, oxygen, remains unchanged, the lower positive charge of the substituted cations result in excess negative charges on clay crystals. 4. Adsorption of cations. As soil colloids possess negative charge, they attract and attach the ions of positive charge on the colloidal surfaces. They attract cations like H, L, Ca superscript 2 and Mg superscript 2. This gives rise to an ionic double layer. The isomorphous substitution in the colloidal particle makes the external and internal layers of clay minerals negatively charged, and these surfaces act as huge anions, which form the inner layer of the double layer. The outer layer is made up of a swarm of loosely held, adsorbed, cations attracted to the negatively charged surfaces. 5. Adsorption of water. A large number of water molecules are associated with soil colloidal particles. Some water molecules are attracted to the adsorbed cations and the cation is said to be in hydrated state. Others water molecules are held in the internal surfaces of the colloidal clay particles. These water molecules play a critical role in determining both the physical and chemical properties of soil. 6. Cohesion, attractive force between similar molecules or materials. Cohesion indicates the tendency of clay particles to stick together. This tendency is due to the attraction of clay particles for water molecules held between them. When colloidal substances are wetted, water first adheres to individual clay particles and then brings about cohesion between two or more adjacent colloidal particles. 7. Adhesion, attractive force between different molecules or materials. Adhesion refers to the attraction of colloidal one materials to the surface of any other body or substance with which it comes in contact. 8. Swelling and shrinkage. Some soil clay colloids belonging to smectite group like montmorillonite swell when wet and shrink when dry. After a prolonged dry spell, soils high in smectite clay, e.g. black soil vertisols, often show cross-wide and deep cracks. These cracks first allow rain to penetrate rapidly. Later, because of swelling, the cracks will close and become impervious. But soils dominated by collinite, chlorite, or fine-grained micas do not swell or shrink. Vermiculite is intermediate in its swelling and shrinking characteristics. 9. Dispersion and flocculation. As long as the colloidal particles remain negatively charged, they repel each other and the suspension remains stable. If on any account they lose their charge, or if the magnitude of the charge is reduced, the particles coalesce, form flock or loose aggregates, and settle down. Th. 367. 2145. Phenomenon of coalescence and formation of flocks is known as flocculation. The reverse process of the breaking up of flocks into individual particles is known as deflocculation or dispersion. 10. Brownian movement. When a suspension of colloidal particles is examined under a microscope, the particles seem to oscillate. The oscillation is due to the collision of colloidal particles or molecules with those of the liquid in which they are suspended. Soil colloidal particles with those of water in which they are suspended are always in a constant state of motion. The smaller the particle, the more rapid is its movement. 11. Non-permeability. Colloids, as opposed to crystalloids, are unable to pass through a semi-permeable membrane. Even though the colloidal particles are extremely small, they are bigger than molecules of crystalloid dissolved in water. The membrane allows the passage of water and of the dissolved substance through its pores, but retains the colloidal particles. Types of soil colloids. There are 4 major types of colloids present in soil. 1. Layer silicate clays. 2. Iron and aluminum oxide clays, sesquioxide clays. 3. Allophane and associated amorphous clays. 4. Humus layer silicate clays, iron and aluminum oxide clays, allophane and associated amorphous clays are inorganic colloids, while humus is an organic colloid. 1. Layer silicate clays. These important silicate clays are also known as phyllosilicates, phyllone, leaf, because of their leaf-like or plate-like structure. These are made up of 2 kinds of horizontal sheets, one dominated by silicon and other by aluminum and or magnesium. 4. Silica tetrahedron. The basic building block for the silica-dominated sheet is a unit composed of 1 silicon atom surrounded by 4 oxygen atoms. It is called the silica tetrahedron because of its 4-sided configuration. An interlocking array or a series of these silica tetrahedra tied together horizontally by shared oxygen anions gives a tetrahedral sheet. Alumina octahedron. Aluminium and or magnesium ions are the key cations surrounded by 6 oxygen atoms or hydroxyl group, giving an 8-sided building block termed octahedron. Numerous octahedra linked together horizontally comprise the octahedral sheet. An aluminum-dominated sheet is known as a dioctahedral sheet, whereas one dominated by magnesium is called a trioctahedral sheet. The distinction is due to the fact that 2 aluminum. 368. 2145. Shankar IAS Academ. Ions in a dioctahedral sheet satisfy the same negative charge from surrounding oxygen and hydroxyls as 3 magnesium ions in a trioctahedral cytete. The tetrahedral and octahedral sheets are the fundamental structural units of silicate clay. These sheets are bound together within the crystal by shared oxygen atom into different layers. The specific nature and combination of sheets in these layers vary from one type of clay to another and control the physical and chemical properties of each clay. Tetrahedron. Octahedron structure. 2 iron and aluminum oxide clays, sesquioxide clays. Under conditions of extensive leaching by rainfall and long-time intensive weathering of minerals in humid warm climates, most of the silica and alumina in primary minerals are dissolved and slowly leached away. The remnant metals, which have lower solubility, are called sesquioxides. Sesquioxides, metal oxides, are mixtures of aluminum hydroxide, LO3, and iron oxide, FeSOG, or iron hydroxide, FeO3. The Latin word sesque means 1 1/2 times, meaning 1 1/2 times more oxygen than L and Fe. These clays can grade from amorphous to crystalline. Examples of iron and aluminum oxides common in soils are gibbsite, L2O3.3H2O, and geochite, Fe2O3.H2O. Less is known about these clays than about the layer silicates. These clays do not swell, not sticky, and have high phosphorus adsorption capacity. 3. Allophane and other amorphous minerals. These silicate clays are mixtures of silica and alumina. They are amorphous in nature. A wet mixture of other weathered oxides, iron oxide, may be a part of the mixture. Typically, these clays occur where large amount of weathered products existed. These clays are common in soils forming from volcanic ash, e.g., allophane. These clays have high anion exchange capacity or even high cation exchange capacity. Almost all of their charge is from accessible hydroxyl ions, O, which then attract a positive ion or lose the H attached. These clays have a variable charge that depends on H in solution, the soil acidity. 4. Humus, organic colloid. Humus is amorphous, dark brown to black, nearly insoluble in water, but mostly soluble in dilute alkali, NaOH or KOH, solutions. It is a temporary intermediate product left after considerable decomposition of plant and animal remains. They are temporary intermediate because the organic 369. 2146. Substances continue to decompose slowly. The humus is often referred to as an organic colloid and consists of various chains and loops of linked carbon atoms. The humus colloids are not crystalline. They are composed basically of carbon, hydrogen, and oxygen rather than of silicon, aluminum, iron, oxygen, and hydroxyl. The organic colloid particle vary in the size, but they may be at least as same as the silicate clay particle. The negative charge of humus are associated with the partially dissociated enolic, O, carboxyl, Cu, and phenolic group. These group in turn are associated with the central unit of varying size and complexity. Difference between organic and inorganic colloids. Humus clay made up of CHO complex amorphous organic colloid, inorganic and crystalline more dynamic, formed and destroyed more. Clays are stable relatively rapidly. Clays have definite and well-known structure, complex structure not well-known made up of CIO. Significance of soil colloids. The organic and inorganic contaminants are often transported via colloidal particles. Majority of surface area and electrostatic charge in a soil resides in the less than 1 size fraction, with particles with radii between 20 and 1000 mm constituting the major part of soil surface area. Since major part of the surface area is in the colloidal fraction of the soil, almost all surface controlled processes including adsorption reactions, nucleation and precipitation involve colloids. In addition to these chemical processes, colloids are mobile in soils, and thus affect not only the chemical transport of otherwise immobile chemicals, but also exert a strong influence on soil hydraulic properties. 2. Ion exchange, adsorption of ions. Ion adsorption and subsequent exchange are important processes that take place between soil colloidal particles, clays, organic matter, sesquioxides, and amorphous minerals, and various ions. Soil colloids serve very much as a modern bank. They are TE sites within the soil where ions of essential plant nutrients are held and protected from excessive loss by leaching. Subsequently, the nutrients can be withdrawn from the colloidal bank sites and taken up by plant roots. In turn, these elements can be deposited or returned to the colloids through the 370. 2146. Addition of commercial fertilizers, lime, manures, and plant residues. The charges associated W soil particles attract ions, simple and complex, of opposite charge. In temperate region soils, negative charges generally predominate on the soil parted colloids, hence adsorbed cations are present in larger quantities than anions. In more highly weathered soils, e.g. in tropics, where 1-type clays and Fe oxides are the most dominant type of colloids, anion adsorption and exchange is relatively more prominent. Ion exchange reactions, CEC and AEC. The ion exchange phenomenon was first identified by Harry Stephen Thompson in England during 1850. When soil was leached, washed, with ammonium sulfate, calcium sulfate were detected in the leachate. The ammonium ion in the solution replaced calcium in the soil. NH4, 2SO4 plus soil Ca soil, NH4, 2 plus CaSO. The process by which ions are exchanged between solid and liquid phases and or between solid phases if in close contact with each other is called ion exchange. The common exchangeable cations are Ca, Mg superscript 2, H, K, NH ***, and Na star. The common anions are SO42, Ci, PO and NO. The ion exchange in soil is due to the presence of residual positive and negative charges or the soil colloids. These residual charges result due to the process of isomorphous substitution and ionization of hydrogen and hydroxide functional groups. The negative charges attract positively charged ions and the positive charges attract negatively charged ions from soil solutions coming in contact with colloids. The ions thus attracted are reversible and are on equivalent proportions. Exchange of cation is called cation exchange and exchange of anion is called anion exchange. The cation exchange phenomenon was first discovered by Thomas Way, 1850. Ion exchange is the second most important reaction in nature. The first one is photosynthesis by green plants. The capacity of the soil to hold cation is called cation exchange capacity. The unit is cmol, P** kg. The capacity to hold anion is called anion exchange capacity, AEC. The unit of expression is cmol, E, kg. 371 kanagraj.bioscience@gmail.co. T. 2146, Y. Soils particles are generally negatively charged and so bind positively charged nutrient ions, cations,